Hello everybody. Welcome to my first stream on RGB addressable LEDs. Thank you for joining me on this, I hope, series of live when I'm going to try to explain you the underlying of every LED driver that we have and to see how we can improve them. So we're going to start from the basics. Really for you to be able to understand what do we do when we drive LEDs, and also how do we get forward from them. So I've made a couple of slides. I know it's going to be a bit lagging at school, but I think it's a bit necessary. Okay, I'm just going to switch my keynote presentation because I went to that. Here it is. Okay, so part one of many, I hope so. First things first. So topics we cover in this live. First, I'm going to present the different type of addressable LEDs. For those who don't know about them, just a quick reminder of the two main different types. How to decrypt the data sheets, which is really important if you want to write a driver. We're going to light our first LED. I've got something to show you. First my panel and then a couple of LED strips like those here and panels, so we can try them out. We're going to see how do we map the memory using a pixel object, or what, if you know FastLED, CRGB object also. So you will understand why it's built as such and what can we do with it. We will create the first drivers. We'll elaborate on the first slide and the pixel object to create the first driver. We light up a panel with a couple of animation. We will talk about LED mapping for a little bit. You will see what we can do and how we can do it quite easily. Also, I'm going to talk about palettes, not the, I would say, fast LED way of palette, but more like for people from the 80s and the Game Boy. What it means to use palette for colors and how you can use it to actually reduce the memory of your LED array. Of course, some more memory consideration and consequences of how we will go. More topics I will try to cover if we have the time, otherwise I will make a new stream for them. Interrupts and timing. That's for those who knows the driver, they know it's really important. Multi-strip, how to manage, why, when, how to put them. The setup of the multi-strips. And what I call hardware transformation. Scrolling, if you've seen a couple of my videos. Rotation and scaling. And I guess it's going to cover a lot about that. I'm trying to have a look on the chat, but do not, if I don't reply right away, just excuse me about that. And also, I hope you will enjoy the show and let me know if you have any comments in the chat. So let's start. Type of addressable LEDs. So you've got two types of addressable LEDs. The LEDs are driven by getting orders bit by bit in form of 1 and 0. So we say 1, 1, 0, 0, 1. And the LED understands that to actually create the colors. That's the basics of LED managing. We have two ways of sending this data to the LEDs. Either clock-based LEDs, like we have APA 102, WS2001, HD17, HD108. How does it work? The chip reads the signal that we send them according to a clock signal. So it looks a bit like this. So you've got at each top of the clock signal, the LEDs reads the value on the meso line, and that get the new and get interpret the value as a signal, like for instance here 1 1 0 1 0 0 1 0. What is good about these LEDs actually that because it's the clock driving the reading of the signal, then you can have really fast signal. When I'm talking like couple of 10 megahertz, maybe like 20 megahertz for the new HD 108. And it's really, really fast for the update of the strip. You've got precise timing driven LEDs. The most common one are the WS2012, 13, 15, the same story. RGB LEDs and the SK1612, which are RGBW LEDs. This one are a bit different in terms of actually driving. That the chip expects you to send a signal at a specific, I would say, pace. And if you don't do that, then the chip won't be able to understand what happens to it. So here, what happens for the WS2012. So we've got one, which is a 0, which is actually a long, a short one, and then a long 0, and the one which is actually a long one and a short 0. But we will get more into that later. For this slide, I'm going to focus on driving the WS2812 because that's the most common used LEDs, I would say. And also they're the most fun to drive because they're the most complicated ones to drive also. So that's what we're going to do tonight. Decrypt the data sheets. So I'm just going to retrieve the data sheets of the WS12. Just give me 2 seconds. So I should have them, but apparently not. So I'm going to bring it to you right now. Sorry about that. Here it is. Okay. I don't see it anymore. Why? Just a minute. There it is. Okay, so now you should see it. So that's a datasheet for the WS2012B. Here we've got what is important here is actually the timing of what needs to be sent in terms of data, and it's below here. Should be peccato. Here they are. Okay. So each LED is actually needs 1,000 to more than 1,000 nanoseconds to be driven, which is really what is important. And what actually leads us to the timing that we will see before. So when you want to drive a LED, you first need to read that really, really carefully to understand exactly what will happen for the LED. You have to also understand that we send first the LED in the green order, then red order, then blue order. That's for the main RGB LEDs. That's why they call RGBs for the color, but they send GRB. If you use to fast LED, you've certainly used the options order GRB. Let's switch back to my presentation. Here it is. So as the LED for 1 byte, you need 1,250 nanoseconds. That means that if you revert that, that means that you sent your bytes at a speed of 800 kilohertz. Or 0.8 megahertz. That's why you see that in the datasheet. That's the time to set the frequency to send 1 byte. The WS2012B expect 24 bytes, so that means 30 microseconds to send 1 pixel. So that's why when you want to know how long it will take to update one strip, you multiply the number of strips by by 30 milliseconds, 30 microseconds, and then you will get the real timing for updating your strip. And it's quite slow compared to what we can have with the clock-driven LEDs. Okay, so I guess now it's time to try to write out the first driver. So what we will do, there are several ways to create the signal for WS2012B. Either you use RMT or PMW. We're going to use SPI. So the SPI is going to give the tempo, and then we're going to send the data according to this tempo. So to be able to cut the signal correctly, I'm going to divide the 1250 nanoseconds into three slides, which means that we're going to have 460 nanoseconds for a high for the 0 instead of 350. But if you look at the data sheet, you will see that there is it's not really precise. You can have a delay of 150 nanoseconds. So we're still in the range of what is acceptable for the LED. So because we sent the clock 3 times faster, so we're going to have to set up a LED at 2.4 megahertz. I'm going to switch. So we're going to go into coding a little bit. So let's get a bit crazy about that. I'm going to shut that on so I get more memory. So what I'm going to do, I'm going to start, here I'm programming on an ESP32, a simple dev board of the ESP32. So the code that I'm going to have is going to be made for ESP32, but you can use it for, but the principle is going to be the same for any SPI command. Okay. So first things first, I'm going to call the drive. So I paste that somewhere here. But just include the music. Coming now. Okay, there should be enough. I'm just going to include the usual for having the unit type. Okay. I'm going to define the pin that I will send, that I will attach my strip to. And we're going to use the default SPI configuration. So it's going to be okay. We're going to define the clock also. Because you're going to use it to actually analyze the signal that we are sending to the board. And the default one should be S19. Okay. We're going to define our SPI host. Because on the, you've got 3 SPI hosts on the ESP32, VFPI, HSPI, and SPI, but the SPI one is used for the flash memory, so you really can't never use it. Okay. So in the setup, I'm just going to open the serial because we're going to use it to actually follow what we develop. Just begin. Simple one. Okay. Now, I'm just going to retrieve, I hope you don't mind, the configuration for the SPI. I will explain to you what the configuration means exactly. Okay, so here the bus configuration that we have. So we're going to use save that. The pin for the output. All the other pins are to -1 because you don't use them, and the num clock also. Just going to define the number of LEDs. So we're just going to start with simple. Let's maybe like 50 lets to start up. That's going to be enough. I will explain later what this number and why it's actually like this. So now I'm going to define the configuration, finalize the configuration of the SPI. Okay, we're going to say mod 0. No. That means that we're going into most significant bit first. I'm not going to use any CS, and the queue size, meaning the number of commands that I will send at once, will be 1. And that is used because we're going to use DMA also to send the data. Now I can do this. Okay, so here what do I do is actually I initialize the SPI, saying that you're going to use DMA. DMA will allow us to actually tell him, okay, you need to send all this data coming from this set of memory entirely without having to repeat every 32 bytes the sending, and it's kind of simplify the explanation. Okay, so that's the first part of it. So now that the SPI is launched, it's done, we have to send some data. I'm just create a transaction for the SPI here, and I'm going to fill out the transaction, and we're going to see the first setup in the loop. So I'm going to create a buffer, which I will call trans data. So that's the data I'm going to send. So it's just going to be nothing special, just going to be an array of, I will explain the number afterwards, but for the moment, just bear with me on that one. Okay, that's good. So now I can just send the data. And normally we should have something good. Okay, let's compile. What am I missing? ESP. Oh, I haven't defined the SPI by itself. I haven't defined the SPI config. I need a handle for the SPI. Here it is. Oh. Should pay more attention about what I'm doing sometime. Let's. Okay, now you should see my my desk. Here is my ESP32, and I've plugged here a simple card to actually gather the data in here, so you can see what will happen. So if I upload the code, and I'm requesting to see what's going on. Compiling the sketch and uploading. Okay. So now if I do this, uh-oh. Something's wrong inside the SPI clock doesn't seem to run anymore. Just a minute. And valid clock speed. What did I put? Oh, sorry. I forgot to add the clock speed of the SPI, so it doesn't work. Oh, it's not the right order. I don't know why that happened, because it's a structure, so the order should not matter that much. But apparently, yes. The CAS actually digital, I would say grabber, like you've got C logic or something like this, which allow you to create any to actually analyze a digital signal quite easily, and it's quite nice. But I don't see the clock signal, and I don't know why. I should be able to see it now. What's going on? I have my SPI. The clock is 19. That's okay. I'll keep that. Unless something is unplugged somewhere. We should have signal normally. Let me check why it does not transmit the data. SPI host, initialize TMA. Let's put that as a global variable. So here the maximum transfer size actually is the number of LED, because for each LED we need to send 24 bits. So that's why I have this 3 times 8 in here. And I hope I'm going to be able to see now. Here is the clock. Okay. So now we see the clock. The clock is running at, here you can see 2.4 megahertz, which is actually what we want to do. So now that we have our tempo, what I want to do is actually to send data according to this tempo. So if I look at what I need to send, if I go back to the data, so we need to send either for a 0, we need to send 1, 0, 0, for a 1, we need to send 1, 1, 0. Okay. So that means that if we want to send, for instance, because we need to start with the green, the red, and the blue, if we want to send the green color, and we want to send, for instance, a 255 value of RGB. So 255, just going to do like this way, maybe I have to write in the comments. So 255 is 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8 in binary. So if I need to send that, we will translate into 110, 110, 110, 110. That's 4 times. By sending that at the tempo of 2.4 megahertz, we will send 255. Okay, but I don't have a press button that allows me to go that fast. So actually, I've created a small function that can take what we need. That can do that for us quite easily. Let me find my function. Chart to see. So I've created a small function that translates a string into a set of beep that needs to be sent to the LED. So let's define our string. So I want to send that. So I'm going to create a simple string. Or I say string to send. It's an array. Char should be a lowercase s, otherwise Java people is going to kill me. Okay, so I want to send green. So I said 110, 110. I'm going to copy that. The 8 bits for the green. Now I'm going to send what's for the red. So for the red is, we're going to keep 110 because we're just going to send green. Okay. And we're going to send the blue value, which is also, we're going to keep the same. So we only light the first LED in red. Okay, and we're just going to tell him afterwards that's the end of the string. Okay. So I'm going to translate this into a signal to be sent. So what this will do, it will transform the string content on a, I would say, signal stream that actually is understandable by the LED. And I'm just going to transmit this information. And let me see what you see. Yes. And normally, I need to turn on my power supply. Yes, better. Let's see. Up. Normally, if everything goes well, on the line below, we should... Oh, template here. Okay. And miraculously, this become red. That's a good part of it. Okay, but I wanted to see... Yeah, here it is. Here you see, here in the signal, you see that we've sent 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, etc., etc. So we sent it correctly. So now we've sent one LED. Let's say that we want to send another LED. We just need to duplicate that. And let's say, for instance, that we want to send red now. So the first one should be... This one should be there. So let's say first LED here. So this way you can understand what is going on. So if first LED, let's say that's R. No, that's green because we sent the green first, then the R, then the blue, then on the second LED, and again the green, which is going to be 0, the R, and the blue values. Okay. Normally the code should take that correctly. Okay. So let's try to light up a second LED. Uploading. The code is uploading right now. And the second LED is red because it's not really stable, it's too light. I should reduce the value of the red. This way. It's going to be a bit less. My desktop camera is not that good, so I don't see it really clearly. I'm just going to turn the light off on the first one. The green's going to become, the first light's going to be black now. So I guess we're going to be able to see the red on the camera. If I remove that, is that better? Yeah, probably not. Yes, you can see it's red, but it's too light. It's too lit, so there is too much light. Okay, now I turn off the first one and I turn not the right LED. That's what I want to do. Yes, if I turn that off, we see better. Okay, so now we have one LED after the other, but of course, we're not going to do that for every LED. So we're going to try to automate what I've done here. I'm not going to write a string for each time I want to write a LED. It's actually 8 by 3 bytes. That's a lot of memory which is needed. So now let's go back to the explanation of this number here. Why is that this number? So for each LED, I need to send 3 bits, and for 1 bit, for a 1 or 0, I need 3 pulses, because that's what we calculated earlier. So that's why the length of the number of bits that we've sent is actually the number of LED times 24 times 3. Of course, if we were using SK6012, the RGBW LEDs, it will be like number of LED times 4, because we've got 4 set of 8 bits, 4 times 8 times 3 also. So I would say the more complex your LED is, the more memory you will need to do that. Okay, that's the basics of doing a LED driver. I hope I haven't lost too many people yet, and we will try to actually create something which is more useful. So first things first, we need to be able to store the information about the LED somewhere. So we know we store the information into RGB, like in the fast LED way. So to do that, that's where it comes from. We will create a structure in C, because that's the easiest way to do it in C. I'm just going to copy it for now, and I will explain. Yes, it's correct. So we call it a pixel, or a RGB structure, whatever you want. It's actually a set of 3 char values next to each other in memory. So we can either call it by pixel between brackets 3, or red, green, and blue. Okay, that's the first thing we're going to do. So now we can create an array of pixels, because now we have defined what a pixel is. We can define an array of pixels, simply like you will define your LEDs. So we do pixel, LEDs, num-LED. Okay, that's the easy part of it. Now what do we need to do? Because in the LED we will store something like, we'll just add something into the constructor of the LED, so it's going to be easier. For those who know C and C++, that's easy. That's allow us to, by doing that, I'm allowed to write this. This line allows me to initialize the structure in such a way. Otherwise, that's not possible. Okay, so when I create, for instance, for the red, I will create a pixel. I'm going to call red. You will be able to pixel. I'm going to put 255.00. Okay, so now in memory, somewhere at address whatever the address is, I'm going to have 1 byte with 255, 1 byte with 250 with 0, and 1 byte with 0. Okay. Now we need to transform that, as I did with the string, into something that actually understandable to be sent by the SPI driver. That's where it comes a little bit funny. So what we call that transformation, transposition. Choose whatever you want as an explanation to do that. So the first things we need to look at is actually that we're sending this amount of data over bytes of 8, over batch of 8, meaning like the first byte will be 100, then 100, then 10. That's 8 numbers. Then the second one, we start with 0, 1, 0, 1, and the last one we'll do 0, 0, that is the transposition of this value into bytes. So I need to recreate, based on the value, what's going to be there. But I know that every time it's starting with a 1, and every time it's ending by a 0. So I don't need to rewrite every time 1 and 0 when I create the array to be sent to the signal to be sent to the LED. So we're going to first start to prepare function. We're going to start to prepare the data to be sent first by updating, creating the first 1 and 0. Here it is. Okay, so how to prepare that? So I'm going to come function, going to prepare data. And what are we going to send him? We're going to send him a pointer to the data that's going to be sent to through the SPI and through the LED. So we have a lot of number of LEDs. So what we're going to do, because if you look at here, we always store on the first byte this number, the second byte this number, and the third byte this number. Okay. So I'm going to take that. As a reminder. So I'm just going to loop through my LEDs to create the number of LEDs in my array. Now what I'm going to do, I know that the first byte of this array each time was going to be this number, then this number, then this number. Okay. So I'm just going to copy and paste this value. Just going to replace that. Here, here, and here. So what have I done here? Actually, my array, every 3 bytes, the first one's going to be this value, which is this one. The second byte's going to be this value, which is this one. And the third byte's going to be this value, which is this one. So I'm preparing the 1 and the 0 that will always be there in my head. Okay? That's the first things we're going to do. Then we have to transform the data. For instance, 255, we need to put the 1 at the right place, etc. So here, for instance, when we have 255, it's actually like 177, this one. We have to put the 1 here, so data will be like 100, 110, and the second one will be 11, then 0, 110, 110. And then we finalize by 10, 110, 110. So if I get 175, I need to change that into that. That's kind of a long procedure to write, but not that complicated to do. So I'm going to write the first part and then I'm going to copy the rest of the code. So now I'm going to call that function, let's say, put byte in stream. Repeat in stream. Okay. And what it's going to take? It's going to take the value that I want to put and the stream. So values I want to put in the stream, and of course a link to the stream I want to put it into. Yeah. Okay. So if my value is 128, that means that the first byte, then I need to add a 0 at the second place. So if I want to send, for instance, 0B, okay, I need my stream to look like this. 1, 1, 0, 1, 0, 0, 1, 0. Okay? Because I added the 1 here. Here. That's what I need to do. So what I'm going to do is actually, if my value contain the byte 1, 2, 3, 4, 5, 6, 7, then the value of my stream has to be updated by the number that actually is the complementary of this one, which is actually 0B, 0, 1, 1, 2, 3, 4, 5, 6. Okay. And if it's not 1, that means actually 0. I need to put a 0 instead. Else, I need to zero out the value. And there is a nice way to do that. That's end with a not. For those who like okay, and just gonna copy that. Okay, that's the not value. So let's spend a bit of time on that one. So here, the value of the byte before we arrived here was the one that we've prepared here. That was the value of the byte. Because that's the first byte of the stream. Okay, 1, 0, 0, 1, 0, 0, 1, 1. If I said if my value is at least 127 or more than 120, more than at least 128 or more than 128, then I will have a 1 here. See, so while and that value will be 1. Then in that case, I add a 1 by doing a OR, logical OR to my value. So now my bytes becomes 0B, 110, 100, 10. Okay. If it's not the case, then I need to zero out this value because I don't know exactly what could have been in a stream unless I clear it. And it stays whatever it is, 10. Okay. And then I do that for every byte for the 8 bytes. So I'm just going to copy the rest of the code because that's nothing really to. From C. And here it is. So normally now I've put one value inside the stream correctly. So now I've put one value, meaning 255 or 128. I need to go through all my stream, all my strip of LEDs to put them inside an array. So that's, I'm gonna loop over it. So I'm gonna, what I call transpose, actually a mathematical term that I'm gonna use. Just going to put that here because I'm going to use it below it. So void transpose data. So what I will need is actually the link to my LEDs. So pixel LEDs. Do that L. And the link to the stream that I need to be put on. So what I'm going to do, I'm going to go through my LED. Okay, I'm gonna do okay, and what I'm gonna do for each value of this pixel, I'm gonna execute this function. I'm gonna put the byte. That's a real byte, that's not a bit. In the stream. Ah, sorry. I didn't see your comments because sometimes the chat is not displaying. I'm just gonna cut that. I think it's better like that. Sorry for that. Okay. I'm gonna put byte in the stream. I need to put first because the red needs to go first. But is store. So I'm going to call the green value, and I'm saying you put that in the stream. Okay. I'm going to duplicate this line. Here. So now I'm going to put red and blue. Okay. But what I need to do, I cannot put them exactly at the same place. So for the stream, I need to move them one byte after the other. So I need 3 bytes for 1 pixel. So I increase the stream by 3 and the stream by 6. And at the end, I need to tell the stream to be increased by 9. Okay. That means at the beginning of my stream, I put the green, then 3 bytes afterwards, I put the red, then 3 bytes afterwards, I put the blue, and I increase my stream, so I advance every time I change late. Okay? So now we're getting there. So I'm just gonna comment that part because I don't need that function anymore. It was just for you to understand how it works in real life. But now we can create something. So let's say that I'm going to create, I need, how many LEDs? I have 256 LEDs in that panel. So I'm going to increase to 256 here. Come on, select that. Okay. I'm going to increase to 256. Okay, so I'm going to create the little train as we usually do, which actually that's the first things that we learn how to do when we blink a LED. So I'm going to need an offset here because I'm going to increase the offset. I'm going to put it to 0. I'm going to define the size of the train. Also 0, no, let's say 12 LEDs, whatever it is, it's not really the matter. I'm gonna erase small. So what I'm gonna do, first I'm gonna clean up my LEDs as usual, memset. So what I do here is actually the fastest way to clean LEDs. Doing a memset instead of doing a loop through all of them and asking for memory. Just a memset that's very efficient in C. And the memset is actually that. The size of what a LED is. So what a LED is a pixel. Yeah, I could have put only 3, and that's exactly the same number because the size of a pixel is 3 bytes. So could have done that, but it's more generic that way, because if you change your pixel definition to be an RGBW or HD108, which is actually 64 bytes, 8 bytes, it's way easier to do it, more generic. So for int e equals 0, we want to train size a plus. What I'm going to do, I'm going to put the let's to e plus offset, and because I cannot write outside of the array, I'm going to just do a mod. This way, even if I go above the array, it will go back to 0. And let's say that I'm just going to put 255. I'm just going to put, but because I want you to be able to see something, I'm just going to put 128, so it's a bit lighter. So once my LED array is created, first I need to transpose metadata within my array. And once the transposition is done, I can display them. I'm just going to put a little delay. I know you don't like delays, but for that, I think it's good. First, I'm going to compile to see if it works, if I didn't make too many mistakes. Good. Let's upload and let's look at that. Reduce the light on this side. Nothing. Oh. Okay. It did not work. First, I need to increase the offset, of course. Otherwise, it's not going to happen. Trans size equal 1. I've sent it. I did something wrong somewhere, but I don't know where. Let's upload that. Oh, I know why. I know what I did. I forgot to prepare the data with the first one and the first zeros. So the LED do not understand anything because we are missing data. So here we need to do prepare data. If we do not add the 1 at the beginning and the 0 at the end, in between the bytes, then nothing's going to happen. With that, the prepare data needs to be done only once. Huh? There is no need to do it every time. And here it is. We've got a running train with LEDs. Let's do it faster. Oh, something strange happened. Oh. Looks like my array is done. I'm going to switch array to see on that. No. I thought I put 250 LEDs. Yes. Something seems wrong because I do not Cool. Why did I go like this? That is strange. I should have seen bring up the way prepare data unless. No, that's correct also. Oh no, here I made a mistake here. Because I need 3 bytes, 1, 3, because I need 3 bytes per LED. And I did it only for 1/3 of the LEDs. I prepared data only for 1/3 of the LED. So let's cross finger, now it's gonna work. And here it is. Going all the way up and down. Okay. Okay, you can say that's not really miraculous, but you've created the first base of a driver. Okay, and we can go around here and change, let's say, offset. Modulo 128, because I don't want it to be too bright. Cosinus of offset. I'm doing whatever comes to my mind. Divided by 128. And for the green, so normally we should see some colors, strange ones, but we should see some colors. Here they are. So we light it up a little bit more. So I think it's nice. Okay, so we've managed to do the first step of the driver. I will have a drink, just water, if you don't mind. Let me know in the comment if I need to go back to some step of what I've taken and if everything is clear for now. Otherwise, I can still come back before I go on with the demo for tonight. Good, that trick is fine for now. Okay, good. I hope you've learned something at least from what you've seen, or it was already something that you already knew and you didn't learn something new about how to drive LEDs and how to start from the basics to what we've done now. I would be interested in knowing. Okay. Sorry for that. Okay, let's go on now then. LED mapping. Okay, let me do something first. So I'm just going to add another LED matrix. I need to put them in the other way. Just because this second matrix doesn't have the other part. I need to put them. Here they are. I'm gonna line that up. So now what happens? I'm gonna have move that around. Yes. The second panel doesn't get lit up simply because I don't have defined enough LEDs for the panel. So let's put it on 12. And if I do that, normally we should get something. The signal should go through both panels. So it's going to go up, up, and down the other way around. So that's how it goes. Okay, that's cool, but that's not really useful, because what I would love to have is actually having the strip going from one side to the other side and come back maybe like this, instead of having two different strips. So that's why we do mapping. So we have there are two ways of doing LED mapping. I'm just going to turn that light up a little bit because you see me better now. There are two main ways of doing that. The first one is actually to create a matrix function which takes X and Y, like you have, for instance, in FastLED, etc. That's good, but there are two main issues with that. The first one is actually that you need a function in the meantime when you do your LED storing to get the right place. So you cannot do any mem copy quite easily. And the second one is actually, it takes time in the processing of the data. And when you have a lot of LEDs, that's a lot of work to do. So what I'm going to present is maybe another way, what we call the hardware way of doing the mapping. Go back to Keynote. Play. Okay, good. Where is my Keynote? Okay. Why can't I see my Keynote live? Just gonna... Okay, here it is. Play. Sorry, there is an issue with my string deb and keynote, it doesn't want to take the I'm going to switch that and go back here. Maybe it will work now. Here it is. Okay. Sorry, I'm going fast because it became too. We've done all this. We've done all this. The light has been done. Now we're going to the LED mapping. Okay. I hope it's big enough. Let's do this. I'm going to do live resizing. Wish I should not do that, I know. But okay. I'm going to fit it to screen because I think it needs to be presented correctly. And I'm going to extend it. Okay, now I should be more readable. Maybe not. Okay, so what we have here is actually the LEDs. So we're going from 0 to 1, 2, 3, 4, 5, 15, 16 on top. 16 here, and then we're going back into 17, 18, blah, 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 and then we go in zigzag. But what we'd like to have is actually the part which actually, it's not big enough. Sorry, just a minute. I thought it would have been bigger when presenting it. So I'm just gonna try to zoom that out. So I'm sure that you can see it. Yes, better like this. Okay, so what we are, that's the way the LEDs are representing from 0 to 15, then 16 on top of it, and you go on your way back 31, 32. That's the LED number because that's a strip which going to zigzag. What we use to represent is actually having 0 to 15, and then 16 back from the left, and 31, etc., etc., etc. Why this numeration is actually easier? Simply because when I am here, when I want to calculate the position of a strip based on x and y, so it's going to be x plus y times the width of my panel. And that's going to give my number. And it's preferable to actually play in terms of x and y and this number here than having to think about back and forth and back, etc. And instead of writing that as a function when you write the LEDs, something like usually you can see a lot of here, for instance, it's going to be like LEDs of map xy, something like this. That's what I usually see. We're going to not do that. We're going to write the LEDs like we were doing a normal Cartesian function, x and y, like you do it. So what I'm going to do first, I'm going to change my function. I'm going to remove my train because I don't need it anymore. And I'm going to define an array. My first array is going to be, I'm going to go back to 256 for my example. I'm going to say let define LED width, and it's going to be 16. Define LED. The one's going to be 16. That's pretty straightforward for now. Okay. And I'm going to create a function that will map this to this. Okay, that's what I'm going to try to do. Okay, so for instance, 0 is going to be, I'm going to remove my head from here. A moment, just going to hide myself. You don't mind. Easy. Okay, so I'm going to go from 0 is going to be 0, 15 is going to be 15. The 16, when I'm called the 16, I need to find the number 31, etc., etc. So let's write the map function. I'm going to remove that so you can see correctly what's going on. Most of you knows exactly what I'm going to do, but I'm going to write it correctly. So I'm going to take as an entry the lead number on my strip, if it's in zigzag, the lead number that I'm going to try to display. So I'm going to call that position. And what I'm going to return is actually the lead that I should be displaying at that place. That means when I'm displaying, when the strip's going to play lead 16, I know that actually in my array, I should look for the lead 31 because that's lead 31, which is there. And maybe I will go back to that. So what I'm going to do, I'm going to say, okay, which is my position in term n, y, and z? So little while is going to be simply your position divided by 16, because that's where you are, because let's do that correctly. And my little x is equal to position modulo the lead width. Okay. So for instance, if I'm trying to call lead on position 25, for instance, then the y will be 1, because that's divided by 16, and the x in that case will be 9. Okay, that means that if I go back to my presentation here, the lead 25 is here. I cannot highlight it, but the lead 25 is here. So we know that on first row, and that the 9's here. But the 15 here, the transposition. You know, I'm not going to go back. If you really need for me to explain that, then I will go back into the explanation. So if the y value is actually a multiple of 2, then it's pretty straightforward. So if that is equal to 0, that means that we are actually on an even row. And on the odd row, it's getting a little bit more complicated, but so I'm gonna do this like this. I'm gonna be really verbosing in the code. New y, new x. You will understand why later on. Okay. New y will not change. Still y. And the x will still be the x. There is no change in that case because we are on the even position. And if I look at my slide, if you look at for every even row, the numbering on each side is actually the same. So that's why I do not change anything. Okay. When I'm transferring on the other one, new y is equal to y always, but the new x is going to be lead width minus x minus 1. If I didn't make too much mistake, okay? So that's my new x and my new y. So now what I have is actually the x and y in this matrix here. So now to get the lead number that I should look to in memory, we just return this. Now I return new y, new x plus new y times let width. Okay? So that means here, if I enter a number in the LED, it's going to look into memory for another place in memory to give me the right LED. So how do I use that? I'm going to use it in my transpose function. And because I don't want to miss it, what I'm going to do, I'm going to copy that function. I'm going to call it transpose data with mapping. So here, normally I'm looking for the LED high, the number of LED high. But now I'm going to say that's not high. I want the map. How do I call that function again? I don't remember. I want the map function of that. Where's my second driver? Okay. So now I'm going to try to demonstrate using a little. So what I'm going to do now, let's see. Oh, I'm going to mix colors. So for int x equal 0, x lower than LED width, plus plus. I'm going to set up the LEDs at position x plus y times LED width. So I'm considering that I have a normal LED array like it was anything else. Is equal to because it's actually 116 to 116. I'm just going to do that. Pixel. I'm going to mix y times 4 times 8 g times 8. Okay, let's see if it compiles first. Nope, of course, because I called ing instead of x and y. And what else do I have? Oh. Stream not declare. What did I do? Strange. I understand the issue. Pixel was not declared. I did something wrong somewhere. I broke something upstairs. 756 times 20, I think. Oh, that's correct. That's correct here too. The structure seems to be also correct. I did something wrong somewhere. Okay, I can't see it right now. I need to see why I can't compile anymore. I guess I created an error when I created the functions, but I can't see where my error is. So it's really in here. Map function in post. That's correct. That's correct. That's correct. If -6 -1, I return that. I've moved the structure definition before the function. Maybe that's why it doesn't like it in C. Yes, that's the issue. So I need to put that. Okay, so that's the one. So I've put back 256 LEDs and I've put an array and we will see what happened. I didn't use the mapping function yet. So let's see what's going to happen. Oh, that's way too bright. That is way too bright. Let's put 4 instead of 8, because you don't see it. I really need to try to do this. Not even. Okay, 2 minutes. I'm going to try to find something to cover it. Okay, even that is too bright. Codecast. So it's not times 8. It's too bright. Let's see times 2. Let's see what's going to happen if I put it times 2 in here. I need a new camera to actually look at my serial monitor. Okay. at the presentation of it. Okay, that's how it looks, but that's not the good look. I really need to find a way to smooth that so you don't have too much light. No, it's not even better. Oh yes, what I need to do with that. Here it is. Maybe this one too. No. Okay. Let's see what happens if I do just Y and Z. That's a yellow here, which is actually too bright. I just cannot cope with it. Okay, that's better. So now that's the way they're arranged. So not what I'm going to do is actually, instead of using transpose with data, I'm going to use transpose with mapping. And let's see how the LED's going to be arranged this time. And you see here you've got a gradient now because I've put my LEDs using X and Y. It's actually the good way to do it. And if I'm not mapping the LEDs, it's not going to look for the right LED to put at the right place. Okay. That was neat, but now I've got two of them. What can I do? So I'm going to say that my 8 now is actually 32. Because I've got 2, and I'm going to just say that my nub LED is going to be something related to that. I'm going to say that to avoid having a couple of problems. Yes, when you do defines and you've got an operation like multiplication or addition, put parentheses otherwise, then because actually it's going to put it's going to replace that in the code. So if you do this, for instance, because sometimes I see people do that, and then X is actually A plus B, and somewhere in your code you've got X equal F times 3. What is going to be is going to turn into X equal A plus B times 3, because it's just going to do copy paste, purely text copy inside of that. So if you want to really avoid that, you should put parentheses. Okay, just as a reminder, because it can bring some error and people are looking for it every time. So now that we've got two, we're going to go from 0 to 5 and 12. We need to change our mapping function. Okay. So if I just let my mapping, I don't do anything into my mapping function, what's going to happen? I'm trying to display 512 LEDs. Okay, that's not really what we're looking for in here. Okay, what we're going to do is actually change this mapping function here. I'm just going to remove that so you can see. I'm going to change my mapping functions to what it is. So if the number of LED, if my position is above 56, that means that I am on this panel here because the first 256 LEDs are here and the second 56 LEDs are here. So if I'm on top of 256, that means I'm on this side. So somehow I'm higher than the other one. So what I'm going to do, I'm going to create a big Y equal positive divided by 256. Okay. And now the position inside the panel, inside of each panel, is actually position in panel is plus modulo 256. Okay, that means that if I'm below 256, the calculation doesn't change anymore. But when I'm above 256, I'm on this panel, okay? And I have the position on this panel. So now I need to redo the same calculation. So now it will depend. Do we want them on top of each other or next to each other? So I'm going to put on top of each other because I put LED 8 to 32. So I do that. So now my new Y is actually added by Y because I'm going to be on top of each other. And because I'm on the second panel, I need to multiply that by 16 because I have 16 rows on my first panel and I'm on the second one, okay? And I need to do that here too. Okay? And if I didn't make too many, 16 because that's LED 8, huh? Okay. Because at the, no, panel 8. I'm going to define one panel 8. I'll define that value too. Because one panel is actually because each panel is actually 16 wide. Okay. So now let's see what's going to happen when I'm going to move that to that. So now I'm still using the mapping function. Let's see the impact of the code that I've changed to my panel. Wow, that's way too bright also. Oh yes, true, because I'm going 16 over 16, so it's way too much. It's way too big. Just a minute. I'm just going to shut it down while I'm correcting the code. First, I'm going to look if I didn't make any mistake. Oh, good. So I'll choose that here first. I made a mistake in my calculation because I still use the old value of the Y instead of the position within the panel of the pixel. Of course, it will not work. So now I'm going to light it up again. And there it is. So normally I should be able to find a way for them to actually mix with each other. Here it is. I've got both of them here. And they match in terms of progression. Okay? Does that mean that if on top of that I had a blue train that goes like this, we're going to be able to see. But what is interesting in doing that, actually now we can display pictures quite easily that we have our mapping function. So I hope Nintendo's not gonna bite me for that one. I'm just gonna take the pictures. Let me find one. Yes. Oh, let's take this one. Okay. Okay, what I'm going to do is just going to add in this file some data outside, because otherwise it's going to be too much. And I'm just going to add and include in here structure. I'm going to do here. Hey. Okay. So now I've included, so for those who don't know, that's a strawberry. But that's not the picture of the strawberry, that's actually the value that I used to map the strawberries. And I'm going to try to define the pixel of the pixel. So I need to find which, for the strawberry, which palette do I use? Palette. Here it is. So that's the palette I used to map the strawberry colors. So that means that when I say 0, that means that's referred to the pixel, to the value 0, 0. When I say 1, it's actually the red. When I said 3 is actually white. And when I said 4 is actually green. And 0, 0 is still 0, 0. Okay. I'm going to add a function that I will explain later. So what does this function do? It's simple. You give it an array of integers. You give it the palette for each color, which is integer, and it gives you back a pictures where everything is actually filled out. So it's going to look for the value of the color inside the palette to give you the full pictures in RGB. It's nice because that means that you don't need to store RGB values. You can only store integer, for instance, and then you will map the palette. Then I need to define too the basic transparent color that I used. No, because I used color here, so okay. So now I can use that to calculate mapping. So now setup function. That will create the strawberry picture. Based on the palette. Okay, now I have the strawberry pictures. I need to be able to display that. So because now I'm just considering now that I'm just considering my array my 2 panels are just a big array of 16 by 32, we can really create a very easy function to actually put the pictures on the map. So we're gonna say display pic. We're gonna say, okay, why is it gonna be displayed? Things y, things x and y. We need to know where it's gonna be displayed. And of course, we're gonna say, okay, give me the position of the array of stuff to be displayed. Picture, and also its size. So int the width and int the height. Okay. And the destination, of course. Okay. So now what's going to happen? We know that the maximum, the x are between 0 and 16, and the y are between 0 and 32. That's what we need to remember. Okay, so because we start at 0, so if x is above or equal to let width, return, because we cannot display that, it's too high. And the same thing for y, let 8. Okay, but the same in the opposite. X is below minus let width, because that means that we will never have 1 pixel on the side, or y minus let 8. Okay, so this way we know that we have to be in somewhere. Okay, so that now the size of what actually is going to be displayed of what we have, I have of what we have. Oh yeah, I'm going to use a strawberry, and then I'm going to use your penguins, but it's a bit harder to display on that one. I'm going to just do that and then display your penguins because they're really cool. But here I can move the strawberry across. Then I cannot really do with your penguins are larger, but I will do that just after that. But just to adapt using the same code, I'm going to put your penguins on the screen. So what did I want to do? So now I need to know what is the size of what's going to be displayed, what's left. Okay, so what's left in X is actually I need to remove. I need to know where I'm going to start for the X. So if my X is positive, I know that I'm going to start from the first pixel, from the start. Yeah, I know I could actually get rid of that if I initiate the start x2 equals 0, but just for the explanation about what I'm doing. Okay, Otherwise, if x is negative, that means that I need the x to start is actually, it's going to be minus my x. Because if I have a size of maybe like 22, and it's not let 8, it's actually the width in here and the 8. Yes, that's more logical. If I have a size of 4, for instance, and I'm at -2, the x is going to be 2. Okay? Okay. And I'm replicating the same story for y. Okay. But now I'm going to add something here. And the int display width, int display y. Okay. What the size of what I'm going to display, because if I'm at some x, it's going to be x minus my the width of the total width. So if I start at 0, for instance, and I'm going to go width, I need to reduce width -8. So I'm going to do this w, it's equal to late width minus width. Okay. So that means I'm going to say, okay, now this is what I'm going to display. If it's positive, that means I'm going to display everything. If it's negative, that let me think I'm doing it the right way or not. Oh no, I need to add that. It's the x plus the width minus the size total. Wow. Yes. Okay. But for the moment, let's say that I'm just going to display it from 0, 0, just to be sure what's going to happen. So let's say I'm going to this w equal just for the chart of the display, then I will move it around. This way I'm sure that it's okay. Okay. So now I'm going to push the ladder. So what I'm going to do is actually for int row, I'm going to go through the different rows equals 0. The row is less than the 8 of the image. Oh, God, so. Then for each row, I'm just going to do a memcopy. Source, destination, and size. Destination, source, size. So I'm going to copy in the destination what I have. So it's actually that my source here, my picture, and with the size, and the size actually width times size of pixel. Okay. Now I need to go forward in my picture, so the pictures I'm going to increase by the size of the width, and the destination is going to increase by the size of the width. Okay, so normally if I do that, what did I do? Where is my setup function? Oh, that's, I move that here. I hope YouTube does not recognize Italian bad words. I create the peak, so now I can move my peak. I'm just put it on 0, 0. In the LEDs. Okay, let's see if it's actually compiling. What's going on? Oh, I didn't take the right one. I didn't take the right palette from my code. And primary expression. Oh, stupid Eve. It's late. I'm doing stupid stuff. No, I don't do all my Fastlet coding in Arduino. I use Visual Studio Code to create most of my driver. And then I write my program using my driver in Arduino. And also I can use, sometimes I use ESP IDF. And if you could see, but it's bright still. Normally, up. Oh, cat. Okay, just gonna do something. I need a new cam for... I'm gonna switch to... Oh, it's OBS. It's here. Okay. So normally, now you can see that I'm displaying a little strawberry on the fly in the image. Yes. I've changed, I've used my phone to actually do that because the camera which I have here needs to be changed because it's not good enough. So now I could actually really easily push an image into my panel without having to think too much about where it actually goes. Because I'm using a mapping function. And if I push it above what it used to be before, so if I do that, the destination plus equal, normally I should go up of the x, y times let width. And I say that I want to display it, for instance, at 8 in height. And I'm going to switch back to my phone camera. Normally, normally you should move up and to the second. Yes, it moved up, and it's in between the two panels. Okay. So now I can move it like I was using a X and Y coordinates without having to think anymore about how it's moved, etc. That's why it's nice to have, I would say, an internal LED mapping function instead of actually what we have usually. That's really, really bad. I don't know what to do about that. Oh, not good. Okay, I need a new camera to. I need a new cam. If I use the cam that's for, no, it's totally plugged to my lap here. It's not going to change. Anyway, maybe if you think it's good that I go on for other lives, I will buy a new camera. And if you want to help me, in the link there is a donation to help me buy a new camera to actually be able to actually tape that. It's a very, very, very bad one and old one. Okay, I guess the first part is done. We are able to start from zero to create a driver for the LED, and we are able to display pictures and do mapping, which is actually nice. But what happens if you have a lot of LEDs and you need a lot of memory? Here, each time I'm creating a LED array, I'm using 3 bytes, which is bad, but not that bad. If I'm using RGBW, I'm going to use 4 bytes for 1 pixel. If I'm going to use HD108, it's going to be 8 bytes for 1 pixel. That's a lot. But if you look at what we've done, in that function, which actually transpose data with mapping, what we do, let me get to that function. I'm going to all my LEDs in my memory, and then I'm saying, okay, take the green part, take the red part, take the blue part of that, and then you do you display that. But nothing prevents us from doing something else. I could actually mix up green and red, or divide green by 2 or red by 2. That's how we do the... that's what I should do here, actually. I'm going to divide by 8 all the values that I get. And normally it should be way less bright. That's how we do the... when you do in Fastlet the set brightness, that's what it does actually within the array. It actually divided the value that you got into something which is actually less. And here it is. Up, I'll reduce the brightness. Still too much for my stupid low cost camera that I bought like for $10 a couple of years ago. During daylight it's okay, but at night it's actually really, really bad. Really sorry for that. And I'm not good enough yet in OBS to actually change it. I will fix that if you think a new session is actually would be actually useful. But except doing the division by 8 to actually reduce automatically the brightness, we could try to say, okay, but now, like for my strawberry here, where I've actually stored not the color of the pixel, but a reference to a palette, maybe I could store a reference to a palette for my entire picture, because I use only 256 colors, for instance, or maybe 4086 or maybe less. So how can we do that using that kind of method? So now I'm going to say that instead of having LEDs here, I'm going to define, where are my LEDs defined again? Go up, go up, go up. Here it is. Now I'm going to say, I want my LED to be not a color, but a reference to a color. Let's, how do I call that? Map? No, let's palette. Okay, so this array here is actually 1/3 of the size of this one, which is actually good. But now I'm going to try to define a palette. Okay, so this time I'm going to define a palette, which is actual colors that's going to be used. And we're going to say, because here we're going to have only 256 colors, I'm going to say that the size of the palette is 256 maximum, but it could be 2, 3, 4. You don't really care about that. I am going to be less. I'm going to do something less. But let's define that as, let's put that as a definition. Define palette size being, allez, 48 for now. I don't care. Okay. First, what I'm going to do is actually tell the driver not to do that, because he doesn't know how to do it, but to look for the palette array with mapping and palette. Okay. Now I'm not using anymore a pixel array, but an array of char, unsigned char, so from 0 to 66. I'm still going through that, but now I need to find the pixel color of the position of my in my array. So I'm going to define a pixel p, which is equal to more or less the same thing. That's going to give me the value inside the array, but I need to find its position. And how did I call that? Here it is. So here what I have done is actually say, now look inside my array, give me the number and find the color value representing that number. And now I'm just not going to call that, but I'm going to call P and P. Okay. So now in my code here, first I need to create a palette because my palette is empty. It's only crazy colors. So void create palette. Pixel array. Okay, so how am I going to define my palettes? I don't know. I have no clue. Let's say it's going to be only a gray. That could be work. That could work. Palette size. Okay, and I'm going to say equal, we're only going monotone, so pixel of as it's I, we're going to 48, so that's going to be good enough. I regular. Okay, so it's only going to be gray. So I'm creating a palette here. I'm going to call that in my setup function. Oh yes, you've noticed that I could have, because palette is actually a global variable, I could have actually inside the create palette function call directly the global variable, but it's not, I don't like to do that because it's not really flexible. That's just weird. Now in my loop, we can let that because it doesn't have any effect anymore. Create mapping and palette. Here I'm going to call let's palette to my trans data. I'm going to remove the display pic for the moment. We're going to see how we're going to use that later. And then instead of doing this, I'm still referring to the same values. No, it's a number, but it's going to be, let's say, x plus y. And I'm going to do, because it cannot go fast on the palette size. I don't know exactly what's going to happen in that one because I've never tried it like this. That's brand new. The rest I've more or less tried it before. Not the strawberry displaying. That I've implemented it inside my virtual driver, so I know it works. The technique works, but I've never done it with the SPI driver. With this SPI driver, implementing it from scratch again, just in front of you. At almost 10 to 1 a.m. Okay. everything looks the same, which is not good. Let's see. How did I create my palette? Palette size. Why? Good. 2 amps. Transpose data with palette. No, normally it should work. Net palette and trans data. Zero, but I guess maybe it's too bright. That's why. Ah, yes, it's way too bright. So let's divide the value. Yeah, well, it's too bright. Because if I do that, you don't see anything anymore. Yes, you could see the variation. Okay. It's not that nice actually. Maybe I'm just going to create a red palette for the moment. Because otherwise my I'm just going to say that the palette is red. Yes. It's a bit better. And if I mix that by palette size minus I, I should get a crossover. You swap to, sorry, I need to read that. No, I don't have a Discord yet, but maybe I will do it. Okay, so here we're back to red to green. I'm just gonna, Flavor Dynamics is very well. I think I was about with framework. I swapped to the TNC4 to do broad first from complex math. Yes, indeed. To drive the LEDs, SP32 is actually a beast. I can do crazy stuff. I will show you just after that. But if you're using floating point operation, the SP32 is not your MCU. Okay, so I've changed the way I've created my palette. It's only 48 colors inside this palette, from red to yellow to green. But what I'm going to do here is actually I'm going to do this. I'm going to create inside my I'm going to create inside my setup the LEDs. Okay. And now what I'm going to do is actually I'm going to add a function to my create palette. I'm going to add one. Okay, so now my palette size is going to be a function of one value. And instead of remapping in the loop, instead of remapping my LEDs, so to move to 12 LEDs, I'm just gonna recreate, change my palette. And for those who are really old school, if you know actually GBA, Game Boy or SNES or whatever calculation and programming, that's how we do animation, fast animation on that one. You don't change it, you actually switch the palette. And here it is, animation, and I'm only moving 48 data because I'm moving the palette and not the animation behind the palette. And I think it's kind of cool to show. So you can actually, with reducing by a third your data, doing some crazy stuff. If you have, for instance, letters which are actually displayed, you can have a rainbow across the letter without having to redisplay the letter. Just move the palette around and it will do it by itself. So hit me up if you think it's nice, if you like it too. But I think it's a nice feature that you can have, first for reducing the size of your array, and second able to do some funny stuff like that. Okay. Okay. Do we have something else in the chat? Sorry, I'm just used to that. Okay, good. Zatrick, do you think I should create my Discord then? Let me know in the chat. The SPI driver is way easier to actually start for people to understand how it works. The iSquares driver allows us to do full parallel output. That's why it's actually a bit more complicated to put into place, but all the principles that I've shown tonight stay the same and will never change. It's not going to change at all. Everything is actually the same. Yeah, thank you. Yeah, I'm just 2 minutes. I'm going to put back my phone because I'm using my phone as a camera to show you something else. I'm back, but not sure if it's gonna work. Yes, I need to move the array around. Okay, here we are talking. So here I'm displaying more than 12K LEDs. What I do to what I'm using here, I'm just going to turn the light on here. Otherwise you see the light. It is kind of bored. Yes, it's not going to display correctly. With virtual LED driver, that's a completely different story. But even if I'm using that, the story behind the writing of that stays the same as usual. How many lines is your program currently? For this one, actually like 220 lines, 220 lines. That's nothing. That's really nothing. That's really nothing. But let me show you what we do when we call about hardware mapping using an example here. I need to find that. Open. Panel. Let's show one. Okay. Let me switch window. Okay. Here is a program that controls the panel that you see behind me. Just to show you the mapping side of it. So what I'm going to do, I'm just say no mapping and that. So here I'm using LED width and LED 8 to display the color of the rainbow in X and Y position. Without mapping, I'm going to try at the same time to frame a little bit better. It was perfectly set up before I had to move my phone to actually capture what's on my desk. Okay, so here you see, that's pretty normal because I've got 48 to 56 by 16 by 16 LED array, and they are not linked to each other correctly. So X and Y position is not good. If you look at that, I have more or less the same as I did earlier. A function that defines that is mapping my panel position, returning depending on the number of the LED. And if now I use this mapping function, I will call what Armod map is afterwards. Just I will come that afterwards. So now it's actually correctly mapped. So now you've got the full rainbow. But if I'm not mistaken, and if I do it correctly, it will actually reduce the size of what I'm trying to display. But first, I need to do, if I do this, like this, I'm going to have quite a surprise. So I'm deciding that I'm going to try to display a 64 by 64 picture on my 128 by 96 panel. So of course, here below, I've got the right because 64 by 64 more or less, but then on top of it, it's simply crap. That is pretty normal. Let me do that now. I've added one LED, and then I'm going to show you I'm going to go deeper next time because it's a bit late to go into that, but what we can do in terms of what I call hardware modification. Okay, so now what I'm going to do is actually call where I am. Now, in this LED driver, what I'm going to implement the next time that we are together is actually what I'm using to do crazy displays that you've seen on my panel. So I'm going to say that I'm going to use scroll map. I'm going to define what's actually the size of my panel and define the size of what I'm displaying inside my panel. So I've got an object which is an offset display. I will explain that later. I'm just doing a demo right now, and then I will show you what I can do with that afterwards. So in my setup panel, I need to do that. Here it is. So I'm telling my panel, by the way, my panel width is actually that. My panel height is equal to 96. But the picture I want to display is actually that, and the height of the picture I want to display is actually that. And now, instead of saying display like this, I say, okay, now you need to display using the options that I gave you for the structure of what I'm displaying inside my panel. And I hope I didn't make a mistake. And here it is, 64 by 64 without too much of an issue. But now my panel is pretty empty. What can I do with that? So I can say, oh, by the way, my image, what I'm displaying inside my panel is not 0 to 0. It's actually 32. And let's go high here also. And normally the 64 by 64 image should, here it is, on top of my panel. Okay, but I can do more than that because I say, okay, it's so nice, but I would like to replicate what I see inside my panel. So I said, okay, I'm gonna enable the fact that I'm displaying yes, you can rewatch the video and it will be nice. Now what I'm going to do is actually up. What I did is my 64 by 64 pictures has been like replicated towards the panel automatically. I can reduce it by 32 by 32 just for you to see. Here it is. But you can also keep the same width and the same height and do something like this. I'm not going to enable that first. I'm just going to say, okay, you've looped, that's good, but also move my display around. And that's what I call hardware scrolling. I didn't move anything. I'm just creating exactly the same image as usual. And I'm just you see, I'm scrolling my image without having to do anything. And if I want to do the loopix, meaning like it's going to replicate in the empty space, it's going to replicate the rest of my picture. So the picture is going to go in loop. And here you see the picture is going to loop forever and ever, and it's going to work pretty fine. Can accelerate the motion. Okay, and I can do more than that, of course, because I can say that I can push, I can also rotate the image. So say 464. Let's see like that. Okay, let's see what will happen if I do that. Oh. Off. Sorry. I missed it. An error. While it's charging, let me look at the chat. Yes, it's a lot of info to take at the first place, but here it is. I am rotating the pictures without too much of an issue. Okay, and I can remove the loopix here just to have those. It looks like it's beating. Yeah, I guess the calculation is, yeah, because I'm getting integer manipulation, so maybe that's why it's not that clean in terms of rotation. But yes. So how I do that is actually the same way I do the mapping as you've seen before, except that we do more clever mapping situation inside the driver. So that's going to be for the next time if you want to. So the topic for the next time would be, as I said, hardware transformation. I just made a demo here about hardware transformation. If you want, I can make a second live next week to explain, to go back to certain topic. If you want to, you can put them in the comments here and go further into the hardware rotation. And then we go back to multi-strip, I2S, and a lot of LEDs, even without any drop of memory. And that's a deal that I've learned. Okay, just let me know if you enjoy the first part. Let me know if you will watch the second part. Let me know what I can improve. I think I need to change my camera to display the LEDs on my desk. That's not good enough at all. Let me know what you liked, what you disliked. I hope this is my first stream, so I don't know if my voice is correct, if I'm speaking too fast, too loud, not loud enough. If the content was interesting, if you learned something, yes, comment, like, like and subscribe, of course. Yeah, I'm gonna wait a little bit with that, so you can let me know. I'm just gonna change the animation on my panel, and I will let you with that for the end. I'm here, yeah, still 10 minutes to answer your question in the chat. Oh, by the way, next topic that we could touch also is the use of the second core for the SP32, because it's fully integrated now in the driver. If you want, we can also discuss about that. Thanks to you for following the stream, Xatric, and NT. Let me know if you think you could, if you would like to see another episode to go deeper into that, because we just had not the surface, but more or less, yes. Yes, I will, definitely, because I don't know anything about Discord, so. Glad that you like it. Okay. I wanted to display something more. You either push me, you can send me on Reddit if you are. I'm HPWET on Reddit. You can have me on Instagram or on Twitter, X now. You've got the link. TechWit on Instagram and on Twitter. You can find me, and then we can share email address to go a bit deeper into the topic. If you like the video, do not forget to share the live. The live will stay on my YouTube channel. And let me know, of course, about the technicality of the stream also, because as it's my first, as I said earlier, I will be happy to hear from you on that part. Thank you for the follow on Instagram. Thanks for the follow. Okay, if no other question, then I guess I will drop for now. I will let my exit pause go. Yes. Coming back soon, of course. If you'd like what I've done, please do not hesitate to donate to my PayPal also to support me in doing those streams and the rest. Otherwise, I wish you the best and see you next time. Bye bye. Yes, I will create a GitHub, especially for that. That's a really good idea. I will not do it tonight. It's 1:30 almost here in Belgium. Thank you, Patrick. I will post that, and we will do. So we'll be able to upload all the different examples that I've made tonight. As I said, do not hesitate to share to all your friends if you think it was interesting. And I will prepare something for somewhere, not maybe next week or the week afterwards. Okay, thank you, bye-bye.